What's up everyone, and welcome to this new section in which we'll build callbacks with TensorFlow. In this section, we'll look at how to build a callback from scratch by inheriting from the callback class. And then we'll build other callbacks made available by TensorFlow like the CSVLogger, EarlyStopping, LearningRateScheduling, ModelCheckpointing, and finally ReduceLROnPlateau callback. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. Callbacks are methods we call during training, evaluating, or prediction. These callbacks can permit us extract useful information from those processes we just listed, or even carry out changes on those processes. Here in this TensorFlow documentation, we have TF Keras, and then we have the callbacks. So this is what we have for the documentation. We could go through each and every one of this, but for the sake of this course, we are going to look at the key ones. So right here we have this callback, but before getting into this, we are going to look at the history. The reason why we're looking at history first is actually because we've used it already. So we use this callback without really knowing that we're using callbacks. So here we're told this is a callback that records event into a history object. So remember the times we were having this here. So after training, that's when we're training, we start some information in this history, and then after training we're able to come up with plots like this because we had this information stored in this history right here. So that said, as you could see in this example, which is kind of like similar to what we've been seeing so far, we have this history and it collects all values we've been storing during training, and then we could print out this params, history.params, we get the params, and then we could also get the keys. So that's how this works. We've seen this already, and then we could look at this callback class right here. Now the reason why this is like the most important of all this different callback classes is because this is kind of like the mother class, or that abstract based class which can be used in building new callbacks. So if you want to build a callback which isn't listed here, you could always get back to this and then build that callback from scratch. So here we have this callback class which has attributes, as you could see, params and model, and then it also has this methods which we'll see how to implement very easily. If you look at this onBatch begin and this onBatch end, you'll see that they take similar arguments. Like here we have the batch, and then we have this logs. Then for the next, the epoch begin and the epoch end, they actually take in the epoch and the logs. That said, we'll import the callback. So here we have from TensorFlow, Keras, callbacks. We're gonna import callback, this class which we're gonna be using in creating our callbacks. We run that. Then we define this callback class, which we'll note as called lost callback. We have this lost callback class which inherits from the callback which we've just imported. And then we will make use of the different methods which have been given to us in the documentation. Let's start with the on epoch end. So on epoch end, we're taking the epoch, and then what we're gonna do is we are gonna print out the lost values at the end of an epoch. So what we'll be doing is kind of similar to what we have already here. So let's do that and have print epoch number, let's say epoch number this, and then has a loss of for epoch number this. Our method, the model, has a loss of this, and then we just format. So there we go, we pass in the epoch. Let's have this here and the logs. So just as in the documentation where we're at in the epoch and the logs. Now we are gonna pass in the epoch and then the logs, but since we want to get just the loss, we could get the loss from this. So we have this dictionary here and we pick out just the loss. Now let's run this, and then we'll see how to include a callback in the training process. So just right here, we're gonna have callbacks. So the callbacks argument, and we have this list. So in this list, we're gonna insert this callback we've just created here. So we have the last callback, which we just pass in here, and that's fine. So now let's rerun this. Let's take this for say 3 epochs and then see what we get. We get in this error. We click search Stack Overflow and then click on this. You'd see that we have a solution just here, and what is said here is what you're gonna pass is the object and not the class itself. So that said, instead of passing the last callback as we just did, we're gonna pass in this object. So we're gonna put in the brackets. Let's modify this print here and pass in a space. So we're gonna have that. So next line, and then we rerun that again. So let's run that, and that's fine. Then after training for over 3 epochs, here's what we get. We see that unlike before where we just had this outputted, now we have this message outputted. That is for epoch number 0, the model has a loss of this, for epoch number 1, and then for epoch number 2. Now what we could do is we could add this, so we have this formatted normally, so we don't start from 0 but instead from 1. So we could say +1 right here. So that's it. Now another thing we could do is we could have on batch end. So on batch end we have that, and then we have the batch. We pass in the locks. This time around what we want to do is kind of similar to what we've seen already here. So we just print this out. That's fine. Take that off. So for the batch number, for this batch number, the model has a loss of this. So there we take in the batch. So that's it. And then we log out the loss. Now, yeah, let's just pick out this logs totally. So we have the logs, and then that's fine. So here we've put in the batch, unlike here we're passing the epochs. We run this again and run this, run this. You'll notice that this time around we have much more information which has been logged out. Let's take this here and get right to the top. What we have here is for batch number 1, the model has this loss. So you see that this is after each and every batch. So here, the first batch, we have this log, and then the next batch, we have this log, and so on and so forth. And since our batch size equals 32, this simply means after working on 32 different data points, we're gonna have this logged out, and then the next 32 we have this logged out right up to the end. Now for the epochs, you'll notice that as we go on, so we're moving on to, let's get right up to 689. We have that, and finally here we have 689. Okay, so for this last year, that's at the end of the epoch, we now have this logged out. So here we have for epoch, whereas previously we had for batch, for all the different batches. In case you want to understand how we got this 689 right here, you could take the total data set size and then divide by the current batch size, which is 32. You should get this 689, which is given right here. So from this, we could look at the CSV Logger. Now with the CSV Logger, what we're actually doing is we're logging out this information in a CSV file or in some file which we're going to define. So what we'll do is just simply copy this. Now this time around we wouldn't actually have to recreate a class as we just did with the callbacks, because this is kind of like a general way of creating this callbacks. Now with the CSV Logger, we'll actually create the callback more easily. So here we have this, and then we're going to specify the file name. So here let's have the CSV callback equal that. Let's take this off, and we'll specify our file name. So yeah, we just have our file logs.csv, and that should be fine. So we take that off, and then up right here we have to import CSVLogger. That's fine. We run that. everything is okay. We get back to our callback, and then we run this cell right here. Now note that this append is, as described in the documentation, a boolean which tells us whether the logs we are currently putting in the CSV file or in the file in general are going to be appended on previously logged content or not. So when we have this as false, we're supposing that this is empty, and so we are going to like be putting information in this file for the very first time. So we've run this, and then now all we need to do to take this new callback into consideration is to have here CSV callback. So let's make sure, let's take this batch logs out from here. So we are not going to take this loss callback into consideration any longer. We run this. After 3 epochs, we're going to open this up, and then we have this logs.csv file which has been created. So let's have that, and as you could see, we have this CSV file which we could now download and then view it later. So here we have the accuracy, AUC, and all the other metrics and loss values which we want to store. So that's fine. Next thing we could do is we could get back again here, and then I'll select append true. So if we've done training the first time and want to redo the training process, we don't want to erase all the values we had previously. So here we set this to append true. Run this again. After 3 epochs, we open this log.csv file, and what do you have here? You see we have this new information which has just been appended on the previous information. From this CSV logger, we could now move on to this EarlyStopping callback right here. To better understand EarlyStopping, let's get back to this plots which we had previously. So let's take out this plot of the model's accuracy, where we see how the train accuracy keeps increasing, while after a certain point, let's say this point here, let's take this off. After say this point, our models, or even this point here, our models validation accuracy doesn't increase any further. So what we have in here is something like this. We have this training accuracy which increases and goes towards 1, and then the validation accuracy which is something like this. Now in some other cases you would even have situations where this starts to drop. Nonetheless, in this case we have this plot where it just kind of like stabilizes and doesn't increase any further. Now note that this kind of situation is known as overfitting. In overfitting, the model starts to overfit the training data. So because the model has been trained on the training data and not on the validation data, at a certain point the model stops or ceases to generalize, because the aim of this training process is not to come up with a model which only performs well on the training data. We're trying to come up with a model which performs well on any type of data, be it the train, be it the validation, or the test data. So if we're able to have a model which does the same, or which has the same performance with the train and with the validation, with the test, then that model is an ideal one. But in this case, we see that as we keep on training, the model's parameters have been modified to suit only the training data. And this is very dangerous, because at a certain point, you may feel like because you're having high train accuracy, your model is performing well. Whereas this isn't the case, because when your model will be shown new data, like the validation in this case and the test later on, this model wouldn't perform as well as it will do, or as well as it's doing with the training data. So to avoid this kind of false measurements, we tend to stop the training once this overfitting starts to occur. So this means that if you training and then your validation, let's suppose we're stopping at this here. So we're training and then your validation data or your validation accuracy seems to be constant, whereas that of the training seems to continue to increase, then it's better for you to stop training at this point, because after this point the model parameters are just been modified to suit the training data and doesn't really generalize, which is the case here, because we're trying to extract some information from this data and make the model intelligent. So the model doesn't become intelligent by only modifying its weights or parameters based on the data it's been trained upon. It's intelligent because after being trained, it can perform well on data it has never ever seen. So here we have this EarlyStopping, where after we notice that the validation accuracy doesn't seem to increase any further, we just kind of like stop the training and then use the model parameters from this number of epochs. So we could say that after say 12 epochs, we just stop the training. Now let's take this off and then replicate something similar for the loss. So if we're having a loss, we could have something like this and then that. So here we have the number of epochs and then we have the loss. So you could have a situation where you're having your training data, which your training loss, which keeps reducing, whereas for the validation, you see, you would have something like this. So this is a typical plot for overfitting. Nonetheless, in our case, the model overfits, but not that much. In some cases, you will have a situation where this even starts to drop and where the loss starts to increase after a certain point. Here is a validation loss, and then here is a training loss. Obviously, the training loss will always keep reducing because we are training on this training data. So what we're saying is, at this point where the validation stops reducing, it's important to just stop this training, and this is known as EarlyStopping. Now, recall that the aim of callbacks is to be able to modify the training process, the evaluation process, or the test process, that's a prediction process, in an automatic manner. So that said, we shall make use of this EarlyStopping callback right here, which will permit us stop training automatically once we notice that a given parameter, like say the loss, the validation loss, doesn't drop any longer. So here we're just gonna copy this and then we just apply it similarly to what we had done with the CSV callback. So here we add this text and then we add that code, we just paste this out. Now we define this ES callback, that's EarlyStopping callback, and then we'll look at the significance of each and every one of these arguments. Now coming back to the documentation, we have this monitor, quantity to be monitored. So by default here we have this val loss. This means that this callback will simply check on this validation loss right here, and then once it stops reducing, like say at this point, we're gonna stop the training. Whereas if we change this to say validation precision or validation accuracy, then what we'll be monitoring will be that accuracy or the precision value. So if you have them like this, we'll see we'll stop around this right here to ensure that we don't go and overfit on the training data. The next argument is this mean delta argument right here. So with the mean delta argument, we are defining a minimum change below which any change is considered as no improvement. So if we're having a loss like this, and that our mean delta is say a value of 0.1, then even if this loss reduces by a value of 0.5, then this callback will consider that there has been no decrease in the loss because the mean delta is 0.1. Now by default, the mean delta is set to 0. This means that any slight change is considered as a drop. So if we have even 0.0005, then we consider this as a drop in the loss. Now this is important because this has a patience. This callbacks make use of this patience. With this patience, we are defining the number of epochs above which, if we don't have a decrease in the validation loss, like in this case of the validation loss, we consider that we could stop that training process. And for the accuracy, is the number of epochs above which, if we don't have an increase in the validation accuracy, if we've picked validation accuracy for the monitor, then we would have to stop the training. So we define this, or we predefine this so that this could run automatically. Now for the mode, by default we have the auto mode, but we could specify min or max. Notice that when speaking about the loss, we spoke of a value or the number of epochs above which, if the loss doesn't decrease. So here we're supposing that the loss is meant to be decreasing, and in that case we are having a mode of mean. Now for the accuracy, we spoke of for the patience, number of epochs above which, if the accuracy doesn't increase. So in this case we're having the max. Now what TensorFlow permits us to do is to use the auto, and with this auto, TensorFlow automatically infers whether it's dealing with a mean or max. So this means that if you place in, for example, val precision, this auto should be able to understand that a precision should be increasing, and so it's going to use a max. Then we move to the baseline, where the training stops if the model doesn't show improvement over the baseline. Then finally we have this restore best weights. With the restore best weights, which by default is false, we are simply saying that the model is going to take up its final state. So this means that if we start monitoring the model, say at this point here, or at this point where we have the lowest possible val loss, and then the model, let's say we have a patience of 5, so we are going to train for further 5 epochs before stopping. So if after 5 epochs we are on this, let's suppose that the 5th epoch we are on this, so we've added from here plus 5 epochs we are on this, and then we are having this loss. It's clear that this model with this loss is less performant than this one. Now if this restore best weight is set to false, then we'll just take the model's weights here, or the model weights which give this loss value here. Whereas if it's set to true, then it means we're gonna take the best weights we've had throughout the training process, and which happens to be the weights which provide this loss right here. That said, here we go. We have this. We have, let's say, the patience to 3, verbosity 1, mode auto, baseline known, restore best weight is false. So let's run that, and then all we need to do is to just include this here. So here we're gonna have ES callback. Now we could take off the CSV callback, but you could always put all this together. Let's just let it, so we could see how all that works. So we just have this list right here, and we have this ES callback with the CSV callback. Now we run the training. We didn't train this for long enough to be able to observe any callback changes. So let's take this to 10 epochs, and then we reduce this to 1 or 2. Let's take this to 2. We run that again, so that's fine, and then we fit our model. After training for 8 epochs, we see clearly here how the early stopping callback stops the training process. Now let's understand why this training process has been stopped. If you take a look at this validation loss right here, you would find that there was a drop here, increase, but after this increase there was a drop, and since the patience is equal to, that's the patience we had defined here, equal to, we have to get 2 successive increases or two successive same loss values before the training process could be stopped. So since after this we have a drop, the training process continues, then we have this increase, and then we have this drop, so it continues. Then here we have this increase, and then here again we have this other increase. So because now we have had this two successive increases, as we could see in the plot right here, you see right here, where we have this increase, drop, increase, and then increase. We now have the training process which is being stopped, as we could see here. That said, we now move on to the learning rate scheduling. Up to this point, we've been used to training our models with one fixed learning rate throughout the process. So we could fix our learning rate as we did to say 0.01, and we use this same learning rate throughout our whole training process. But it happens that if this learning rate is too large, then we risk diverging. And if the learning rate is too small, it would take too long for our model to converge. So let's consider this plot right here. It's actually a very simplified plot, as actually what really happens is way more complex than this. So let's consider this plot, and we have this, and here we have the loss. Recall our aim and the weights. So here we have loss and then weights or parameters, and our aim is actually to modify this weights such that the loss is minimized. So our aim is to get to this position right here. Now we start with a case where we have a high learning rate. So if we are dealing with a high learning rate, then it will be easier for our model to find its way to this minimum position right here, or to some position close to this minimum position, let's say at this point here. But the problem here is, once it gets to this position, it could also very easily diverge from it. So you could very easily get back to another point around here, and then repeat this kind of process again, where the model just kind of diverges. So you could have something like this. It could come down here and then get back to some point around this, and so on and so forth. So we may have this case where the model doesn't really converge because the learning rate is too high. And then for the small learning rates, we may start training, and then if say the model, or if we find ourselves at this point here, that is, we've modified the weights such that the loss value happens to be at this point here, it becomes difficult for us to get to this ultimate or global minima, since the learning rate is too small and the changes we're making are very small changes. So we may find ourselves just staying around this local minima here instead of going towards this global minima, which is this. And so to bring in a balance, what we could do is, when we start the training process, we could use a relatively high learning rate such that the model kind of approaches this global minima faster, and then after a certain number of epochs, we start or we modify the learning rate such that it becomes, or it takes in very small values. And since it now takes in small values, we now start taking up very small changes such that we can get towards this global minima now without risking divergence. Now, one way of doing this is by, say, you could fix, let's say you could suppose that for the first 10 epochs you train your model at a learning rate of say 0.1, and then from 10 to 20 you're going to train the model at a learning rate of say 0.01. Let's say we're dividing by a factor of 10, so we now move to 0.01, and the next 10 again, let's say we're training all this for 30 epochs, and then the next we go to 0.001. So you could train your model, and then after 10 epochs you restart the training by modifying the learning rate in your optimizer, and then again you do this same year. But now the problem with this is, you always have to be there to ensure that after the training, that's after the 10 epochs, you modify this manually. Now, what if we're able to do this automatically? As usual, this is made possible by TensorFlow callbacks. With this callback, that's the learning rate scheduler callback, we could define a function which takes in the number of epochs and then modifies the learning rate based on the current epoch, or based on a mixture of the current epoch and some predefined function. So as you could see here, we have the learning rate scheduler. It takes in a method schedule, and then we could specify the verbosity. Now, this is an example of this scheduler method which has been defined here. Here, what it do is, if the number of epochs is less than 10, then you're gonna use this predefined learning rate. And then in the case where the number of epochs is greater than or equal 10, then we start to reduce this learning rate in an exponential manner. So there we go. Let's take this off. Now what we're saying here is we're modifying the learning rate such that after that we're having before 10 epochs, we're having this fixed learning rate. That's it. And then after this, we start to reduce this. So the learning rate starts dropping as we continue with the training. So now we don't really need to be monitoring the training manually, because this callback will automatically modify the learning rate for you. We could simply copy out this example which has been given to us right here and then make use of it in our training process. So here we have to include this text and then our code. So here we paste out this scheduler. Let's delete this. And then for this one, we have our learning rate scheduling callback. So learning rate scheduler. And then we do this import. So here again, we just have learning rate scheduler. We run that and then get back to this position right here. Let's do this 1 2 3. So that's fine. So notice that here we have this ordered. So we have the callbacks, learning rate scheduler, and we have CSVLogger, EarlyStopping, learning rate scheduler under the callbacks. So that's fine. Let's get back to that, and then we are gonna define. So here we've had the learning rate scheduler, or this scheduler method, but we're yet to define our learning rate scheduler callback. So we have our let's say scheduler callback equals learning rate scheduler, and then it takes in this scheduler method right here. So that's fine. Notice how the scheduler method takes in the current epoch and the current epoch number and the learning rate. So here we have this given to us already, and so we'll modify this to take, say for example, 3. So after 3 epochs, we're going to modify the learning rate, and then we could print out the learning rate. So we could say, for example, the current learning, or actually what we could do is, let's take this off. Let's not have that. Let's specify the verbosity to be equal 1. So here we have the verbosity specified as 1, and then we'll take off this. So you could also check out the CSV logger, the logged CSV file. So you'll notice how throughout we've been logging these values, since we're just adding up or stacking up the values on the previous values we've had already. So for now, what we could do is take this off. Now let's take this off, all this, and then focus on just the scheduler. So we have scheduler callback, and that's fine. Let's ensure that the cells have been run already. So that should be okay. Now we're having this error, verbosity, unexpected keyword arguments. Let's get back to this here, and then we have always variables. So let's modify that as variables equal 1. We run that again. That should be fine. Now we could now get back to our training. So we're expecting that below 3 epochs, let's say equal 3 epochs, we have a given learning rate, and then above that we have a learning rate which decreases exponentially. So that's it. you see here that as the training process starts, we did not really need to print out any value, because when we set our variables to 1, it outputs this. So here we have learning rate scheduler setting the learning rate to 0.00999. That's practically 0.01, which is what we had given here in this learning rate. So it's practically this learning rate setting, and then as time goes on, it's going to decrease this value and then always output the current learning rate. So as we carrying out this training process, recall that the aim of having to work with this kinds of learning rate schedulers is that we want to actually get the best of both worlds. So what we want is speed, because a very slow or a very small learning rate doesn't assure speed, and so we want speed, and then we also want stability when training. So because we want this tool, we are going to use modify our learning rates such that we always get this throughout our training process. And so that's why whenever we're starting with training, we have high learning rates, which could ensure speed. And then as soon as we've trained for a given period of time or for a given number of epochs, and that we're trying to approach this global minima right here, we now seek for stability by reducing the learning rate such that we don't get to this point and have to diverge. So if we want a more stable kind of training process, what we do is reduce this learning rate. After the training is complete, here's what we get. You could see that we have this learning rate, which is now modified after a given number of epochs. So here you see how the learning rate starts decreasing as we go on with the training process. And so that's how we implement learning rate scheduling. But before moving on, let's check out this tutorial provided by the MXNet project developers, which talks of other different learning rate scheduling techniques. So here we have this learning rate scheduling with warm-up. Here it says slanted triangular, and as you could see, the learning rate actually falls between these two values here. So we have our learning rate between 1 and 2. So you could always define your max learning rate and then your mean learning rate. So you could always have this, and then with the warm-up, what we do is we are going to increase this learning rate linearly up to the max for a given number of epochs, and then once we attain this, once we get to this number of epochs, we now start decreasing this learning rate. So here the decrease is linear, so it's a linear function we're using, and then once it gets to the minimum learning rate, we just maintain that constant value right up to the end. So another learning rate scheduling technique we could use here is we have this linear increase, that's the warm up, and then we decrease this exponentially right up to this minimum value. Now this technique of warm up was developed in this paper by Priya Goyal et al, and they found that having a smooth linear warm up in the learning rate at the start of the training improved the stability of the optimizer and led to better solutions. Then from here we move on to the cosine aligning scheduling method, where there is this smooth decrease in the learning rate, which is kind of resembling the cosine function. Now this is what a cosine function actually looks like. So here we have this and that. So here is our cosine function, and then if you notice, you'll find that this portion actually looks similar to what we have here. And now after we get to a given number of epochs, we just maintain that. So we have defined the mean and then the max, and then once we get to the mean, we just maintain that mean throughout. Then we also have this stepwise decay scheduling. Let's take this off. Here you see how we start with a warm up. So this warm up is kind of like a method used very much in practice, and then from here we have this stepwise reductions. So we go in for this fixed learning rate. After a given number of epochs, we now drop the learning rate, and then we drop it, and so on and so forth. So here's our stepwise scheduling with warm up. Then from here we have this cool down, where we follow the stepwise method, and then after a given number of epochs, we now reduce the learning rate linearly, hence the term cool down. We also have this one cycle scheduling technique proposed by Leslie N. Smith and Nicolai Topin. And here's what it looks like. You see that we increase, that we have this warm up and then this linear decrease. Once we get to this initial position, we also have again this linear decrease with a different slope, with a smaller slope. And then once we get to this minimum, or this final minimum, we now just maintain the learning rate. Now finally we have the cyclical scheduling methods, originally proposed by Leslie N. Smith. The idea of cyclical increasing or cyclically increasing and decreasing the learning rate has been shown to give faster convergence and more optimal solutions. So as you could see here, we are having the learning rate, which is going to be bouncing from the minimum to the maximum, as you could see here. So we have this linear increase to the max, and then linear drop, linear increase, linear drop, and so on and so forth. And then finally we have this cyclical cosine annealing scheduling right here. We see how we have the cosine annealing, and then we have this full cyclical process as we go from the highest to the lowest, and then this next cycle from the meet between the mean and the max, that's this, right to the mean learning rate. And then we take up this final cycle from this quarter of the total. So we had 0.5, which is a quarter of 2. So we start from this and then right to the mean. Now notice also that as we are going through the cycle lengths keep increasing. So we move from this to this length and finally this length. Based on the scheduler you want to implement, all you need to do is to modify this scheduler method right here. The next callback we'll be looking at is that of model checkpointing. In this model checkpoint callback, we are able to save the model's weights at some frequency. So unlike previously where after training, like with this, after training our model, we get to we get to save the model like here. So here we saved our model, or we save our weights. After we're done with the training, here we could be doing this weight saving during the training process, and thanks to this model checkpoint callback. Now as usual, we just copy this, and then we could check out on this documentation for the significance of each and every one of those arguments. Here we have the file path. So this is the file where we are going to be saving our model. So here we have our checkpoint callback, and that's it. We have model checkpoint here. We're going to define this file path, and then what are we going to be monitoring? We're going to be monitoring the validation loss, which is what's given to us by default. Just like with the EarlyStopping, where we had this monitor right here, we are going to look at our validation loss. And supposing we have this validation loss and then our training loss. So we're going to look at our validation loss, which is this, and then save the model weights when we have this minimal or the smallest validation loss right here. And then if you set the save best only to true, then we'll save only this weights. Whereas when it's false, we'll save this and also save the latest weights. And then for this argument save weights only, if it's set to true, then we're gonna save only the weights. Whereas if it's set to false, then we're gonna be saving a model. That's a full model with its parameters. Then we'll have the mode, which is automatic. Like since it's validation loss, since it's a loss, automatically this will be a mean. Whereas if this is an accuracy or precision, we're gonna have a max right here. So let's take this back to auto, and then we have validation loss. Now the save frequency when set to epoch simply means we're gonna do the saving after each and every epoch, but we could modify this to say 3. So after 3 epochs, we're gonna verify if our current model is the best of all the previous models. That's if we've set this to true. So if we've set this to true, we're gonna verify if this model, the current model, is the best. If it's the best, then we overwrite this file path. That's overwrite the file, the weight file we've saved. And if it's not the best, we continue training. So that said, let's modify our file path, and then let's call this checkpoints. That's it. So we have this checkpoints, and then we run this cell. We have that, and then we add this callback right here. So we have the checkpoint callback. That's fine. We run the training now and see what we get. After training for over 10 epochs, we have this 2 logs which you could notice here. This one where we've been told assets written to checkpoints assets. So you could open up this checkpoints here, and then you see that we actually saving this model. And then we also have this logged here, that's after the seed epoch. Now let's understand why this logging is done after the first and also after the seed epoch. Just when training starts, we have a validation loss of 0.47, and so we're supposing that since this is the first, then the model is at its best state. Then it moves to 1, which is greater than this. So the model state, or the best state, is this one after the first epoch. This, the model, the first epoch, or the model state of the first epoch is to the best. This doesn't beat the record. This doesn't. And then you'd see that here we have this validation loss of 0.24. That is why the model is now saved. From this model checkpointing section, we'll look at the reduce learning rate on plateau. And then later on, we'll have a dedicated section for TensorBoard. The way this learning rate, or rather reduce learning rate on plateau works is that if you start training with a fixed learning rate, and then say you've trained for over 100 epochs, and that the model performance after 110 epochs, so let's say we have 110 right here. So after this 110 epochs, our model performance doesn't improve. So we still fix our learning rate. But since for the past 10 epochs, we haven't had an improvement in the model's performance, what we'll do is we'll reduce the model's learning rate by a given factor. So here is the factor, the patience. Our patience here is 10, meaning that we're going to wait for 10 epochs before deciding whether we're going to reduce the learning rate or not. The verbosity, as usual. The quantity to be monitored, in this case, the default is the validation loss. The mode, automatic. So if you want it to be mean, you could specify mean or max. But setting it to automatic allows TensorFlow to automatically decide whether it's a mean or max. In the case of validation loss, obviously it's going to be a mean, since our aim is to reduce the validation loss as much as we can. Then we have the mean delta, which takes in a default value of 0.0001, and this means that if after say 10 epochs we have a change in the validation loss, but this change is less than this mean delta, then we'll consider that that isn't a change, and hence we are going to still reduce the learning rate by this factor right here. We also have the cooldown, and then the minimum learning rate below which we wouldn't want to drop our learning rate. As described here, this cooldown is the number of epochs to wait before resuming normal operation after the learning rate has been reduced. We are going to create this callback very easily, and this time around we're going to monitor the validation accuracy. So if the validation accuracy doesn't increase after 2 epochs, we are going to reduce the learning rate by a factor of 0.1. meaning that if we had a learning rate of say 0.01 and that this validation accuracy hasn't increased after the 2 epochs, we are going to reduce this such that this becomes 0.01 times 0.1, which is this factor right here. Just as before, we are going to add this plateau callback and then train our model. After training for 5 epochs, we can observe that we have this learning rate which has been reduced after the 3rd epoch, and this is because after these 2 epochs there is no improvement in this initial validation accuracy, and so that's why the accuracy is going to drop from 0.01 to 0.001. Now that's it for this section. Thank you for getting up to this point, and see you next time.